Pluto sits 3.7 billion miles from Earth. It took NASA's fastest spacecraft 9.5 years just to fly past it. Not to stop, not to orbit. Just to take photographs at 31,000 miles per hour and keep going, because stopping at Pluto is a problem so severe that no space agency on Earth has ever solved it. The sunlight there is 900 times weaker than what reaches your backyard. A message home takes 5 hours to arrive. A reply takes 5 more. And that is just the beginning. Because everything about Pluto, its distance, its darkness, its silence, makes it the clearest example of a destination you can imagine visiting but could never return from. What makes Pluto a one-way trip is not what you think. If this kind of deep science storytelling matters to you, go ahead and tap like and subscribe. We try to cover space the way it actually works, not the way it looks in movies. Are you comfortable? Let's begin. In 1930, a 24-year-old Kansas farm boy named Clyde Tombaugh sat alone in an unheated dome at the Lowell Observatory in Flagstaff, Arizona. His job was monotonous and physically exhausting. Night after night, he photographed tiny sections of the sky through a 13-inch telescope, then spent his days hunched over a device called a blink comparator, flipping back and forth between 2 photographic plates of the same star field, taken days apart, searching for anything that moved. Stars do not move against the background on that timescale. Planets do. On February 18th, he found it. A faint point of light had shifted position between the 2 exposures. It was extraordinarily dim. It was extraordinarily far away. And for the next 76 years, the world would call it the 9th planet. Pluto entered human consciousness not as a world of data and measurements, but as a character. It had a name borrowed from the Roman god of the underworld, suggested by an 11-year-old girl in Oxford, England, named Venetia Burney. It had a symbol. It had a story. The tiny, distant wanderer at the edge of everything known. For decades, it sat in every classroom solar system poster, every textbook diagram, every plastic desktop model of the planets, always last, always smallest, always farthest out. And because it was so far away and so faint, almost nothing was known about it. It remained a mystery wrapped in distance. That mystery was part of its charm. Children grew up learning Pluto's name alongside Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. It felt like a member of the family, the smallest sibling, the quiet one, at the back of the room. And because nobody had ever seen it clearly, people filled the silence with imagination. Pluto became a symbol of the frontier, the place we had not gone to yet. The final stamp in the passport. In 1991, the United States Postal Service issued a series of stamps celebrating NASA's exploration of the solar system. Each planet got a stamp featuring an image of the world alongside the name of the spacecraft that had visited it. Mercury had Mariner, Venus had Magellan, Mars had Viking, Jupiter had Pioneer. Saturn, Uranus, and Neptune, each one paired with a spacecraft that had made the journey. Then there was Pluto. The stamp showed a featureless orange circle, no image, no spacecraft. Just 2 words printed beneath it. Not yet explored. Those 2 words became a rallying cry. Scientists pinned that stamp to their office walls. They slid it into the opening slides of conference presentations. They carried it into meetings with NASA administrators and congressional budget committees. It was not just a label. It was an accusation. Every other world in the classical solar system had been visited by a machine built by human hands. Pluto had not. And for the researchers who had spent their careers studying the outer solar system, that felt like an open wound. The push to send a mission to Pluto began almost immediately. a young planetary scientist named Alan Stern, who would eventually become the most persistent and vocal advocate for Pluto exploration, helped form a group that called itself the Pluto Underground. The name was a deliberate echo of the Mars Underground, another group of scientists who had successfully lobbied for renewed Mars missions after the long drought following Viking. The Pluto Underground wrote letters. They gave talks. They argued at conferences. They pushed concept after concept through NASA's planning system: Pluto Fast Flyby, Pluto Kuiper Express, Pluto 350. Each proposal had a different name, a different architecture, a different price tag, and each one, for years, was rejected, delayed, or cancelled outright. NASA killed the Pluto mission 3 separate times in the early 2000s. Each time, advocates fought it back to life. The political battle to get a spacecraft approved for Pluto was one of the most intense in the history of planetary science. It took more than a decade of lobbying, multiple redesigns, and direct intervention from the United States Congress before the mission that would eventually fly received its funding. That mission was called New Horizons. It was built at the Johns Hopkins University Applied Physics Laboratory, led by Alan Stern as principal investigator. It was small by spacecraft standards, roughly the size and shape of a grand piano. It weighed about 1,054 pounds. It carried 7 scientific instruments, a small nuclear power source called a radioisotope thermoelectric generator, and a small portion of the ashes of Clyde Tombaugh himself. On January 19, 2006, New Horizons launched from Cape Canaveral on an Atlas V rocket. It left Earth faster than any spacecraft in history. Within 9 hours, it had already crossed the orbit of the Moon, a distance that took the Apollo astronauts 3 days. It screamed outward at roughly 36,000 miles per hour relative to Earth. In February of 2007, it swung past Jupiter, using the giant planet's gravity to add another 9,000 miles per hour to its velocity and shave 3 years off the trip. Then it went quiet. For most of the next 8 years, New Horizons cruised in electronic hibernation, waking periodically for system checks, drifting through the emptiness between Jupiter and Pluto with almost nothing to do. On July 14, 2015, New Horizons reached its target. It flew through the Pluto system at roughly 31,000 miles per hour, passing within 7,800 miles of the surface. The encounter lasted hours. The spacecraft's cameras and instruments recorded everything they could, filling onboard memory with data that would take 15 months to transmit back to Earth. And when the first high-resolution images arrived, they changed everything. Pluto was not a dead, featureless ball of ice. It was alive. Not biologically alive, but geologically alive, in ways that no one had predicted. The most striking feature was a vast heart-shaped plain on the surface, bright white against the darker terrain surrounding it. Scientists named the western half Sputnik Planitia. It was a basin roughly 600 miles across, filled with frozen nitrogen ice, divided into polygonal cells that resembled the top of a slowly boiling pot. Those cells were convection patterns. Warm nitrogen ice was rising from below, spreading across the surface, cooling, and sinking back down at the edges. The ice was moving. On a world 4 billion miles from the Sun, in temperatures hovering around minus 387 degrees Fahrenheit, the surface was churning. Around the edges of Sputnik Planitia, mountain ranges rose to heights of 11,000 feet. These mountains were not made of rock. They were made of water ice, frozen so completely at Pluto's temperatures that it behaves like solid stone. The mountains appeared to be floating in the denser nitrogen ice of the basin, like icebergs in an Arctic sea. Except the icebergs were the size of the Rocky Mountains, and the sea was frozen nitrogen at 40 degrees above absolute zero. There were glaciers. Frozen nitrogen flowed through valleys and across plains in slow-motion rivers, carrying debris and carving channels into the surrounding terrain. There were possible cryovolcanoes, features that looked like volcanic structures, but instead of erupting molten rock, would erupt mixtures of water ice, ammonia, and methane. One candidate, a feature called Right Mons, stood roughly 3 miles tall and 90 miles across, with a central depression that resembled a volcanic caldera. If confirmed as a cryovolcano, it would be one of the largest volcanic structures discovered anywhere in the outer solar system. The atmosphere was thin, but real. Nitrogen gas, with traces of methane and carbon monoxide, extended more than 1,000 miles above the surface. Haze layers were visible in backlit images, stacked in delicate bands like the rings of a tree, stretching up to an altitude of roughly 100 miles. The haze particles scattered sunlight in a way that gave Pluto a faint blue sky when viewed from the right angle. Tholin compounds, complex organic molecules formed by ultraviolet radiation breaking apart methane and nitrogen in the upper atmosphere, drifted downward and coated the surface, giving some regions a reddish-brown tint. Charon, Pluto's largest moon, was its own revelation. Roughly half the diameter of Pluto itself, Charon was the largest moon relative to its parent body in the entire solar system. The two are gravitationally bound in a permanent mutual embrace, forever facing each other, orbiting a shared center of gravity that sits in the empty space between them. Some scientists preferred to call them a double dwarf planet rather than a planet and a moon. Charon had a massive canyon system stretching across its equator, deeper and longer than the Grand Canyon on Earth. Its north pole was stained dark red by tholins that had escaped Pluto's atmosphere and been captured by Charon's gravity. There were signs of ancient cryovolcanic resurfacing. And there was a tantalizing question that New Horizons could not answer. Did Pluto have a subsurface ocean? Certain features on the surface, particularly the way Sputnik Planitia seemed to align with the tidal axis between Pluto and Charon, hinted that something liquid might be hiding far below the ice, insulated by the sheer thickness of the frozen shell above it. A world with an ocean, even a buried one, even one sealed under miles of ice at the edge of the solar system, is a world that commands attention. The images and data from New Horizons did something that no amount of advocacy or argument had ever accomplished. They made Pluto real, not a dot in a telescope, not a circle on a poster, a place. A world with weather and mountains and glaciers and color and complexity, the kind of place you could imagine standing on, the kind of place that made you want to go. And that is exactly where the danger begins. Because there is a detail about the New Horizons mission that most people gloss over. A detail so important that it defines everything that follows in this story. New Horizons did not stop at Pluto. It could not stop. The spacecraft flew through the Pluto system at over 30,000 miles per hour and kept going. It is still going now, heading outward into the Kuiper Belt, receding from the Sun at roughly 3 astronomical units per year. As of late 2025, it was more than 60 times farther from the Sun than Earth is, roughly twice as far as Pluto was when New Horizons flew past it. It will never return. It was never designed to. The reason is not a design flaw, it is physics. To stop a spacecraft at Pluto, you have to cancel the velocity that got it there. You have to carry enough fuel to decelerate from interplanetary cruise speed to something slow enough to be captured by Pluto's gravity. And Pluto's gravity is extraordinarily weak. The surface gravity of Pluto is a fraction of even the Moon's. Its mass is only about 1/5 of 1% of Earth's mass. There is almost nothing to grab onto. A spacecraft arriving at Pluto at high speed cannot rely on the destination's gravity to help slow it down the way missions to Jupiter or Saturn can. It has to do virtually all the braking itself, with its own engines, using fuel it carried from Earth. This is where the rocket equation enters the story. And the rocket equation is merciless. Tsiolkovsky's equation, named after the 19th century Russian pioneer of astronautics, describes the relationship between a rocket's velocity change, its exhaust velocity, and the ratio of its fueled mass to its empty mass. The critical insight is that the fuel required grows exponentially with the velocity change demanded. If you want to go a little faster, you need a lot more fuel. If you want to go a lot faster, you need an absurd amount of fuel. And if you want to not only get to Pluto quickly, but also slow down when you arrive, the fuel requirement does not simply double, it compounds. Because the fuel you need to decelerate has to be accelerated to cruise speed first, which means you need fuel to carry the fuel to carry the fuel. Each additional requirement cascades backward through the equation, multiplying the mass at every stage. New Horizons avoided this problem entirely by not stopping. It was a flyby mission. Everything it learned about Pluto was gathered in a window of hours as it screamed past at a speed that would cross the continental United States in about 5 minutes. The decision to fly by rather than orbit was not a choice between two comparable options. It was the only option available with the propulsion technology that existed in 2006, and that still exists today. Putting even a small robotic probe into orbit around Pluto is a problem so difficult that no space agency has ever done it. There have been proposals. The most detailed was a study led by Alan Stern and a team of engineers who designed a Pluto orbiter concept that would use a nuclear electric propulsion stage combined with chemical braking to achieve orbit insertion. Their design required one of the most powerful rockets ever conceived for the launch, a Saturn V class vehicle, a gravity assist from Jupiter, and a spacecraft more than twice the mass of New Horizons. The mission would take roughly 25 years from launch to orbit insertion, 25 years for a robotic probe. And the key breakthrough that made even this theoretical design feasible was the realization that Charon's gravity could be used for repeated orbital adjustments once in the Pluto system, similar to how the Cassini mission used Titan's gravity to maneuver around Saturn. Without Charon, the fuel cost of an orbital tour would have been prohibitive even in the concept phase. A more recent proposal, called Persephone, envisions a Pluto orbiter with a mission duration of approximately 31 years, including a 28-year cruise phase and a 3-year orbital study. 31 years. An entire human generation from launch to the completion of primary science operations, and Persephone is a robotic mission. There are no astronauts aboard. There is no life support. There is no food, no water recycling, and no radiation shielding for human bodies. Just instruments and a power source and a communication antenna pointed back at a planet that would be, by the time the mission ended, populated by people who were not yet born when it launched. This is the first layer of the trap. Pluto feels close because we have seen it. The images from New Horizons are so vivid, so textured, so filled with recognizable geology that the mind makes an unconscious leap. If we can photograph it this clearly, we can get there. If we can see mountains, glaciers, and haze layers, we can visit. The pictures collapse the distance. They make Pluto feel like a neighbor. It is not a neighbor. Pluto orbits the Sun at an average distance of roughly 3.7 billion miles. Its orbit is eccentric, swinging as close as 2.8 billion miles at perihelion and as far as 4.6 billion miles at aphelion. At its current position, light from the Sun takes approximately 5.5 hours to reach it. That means if you could somehow stand on the surface of Sputnik Planitia and look up at the Sun, You would see a point of light so diminished by distance that it delivers less warmth to Pluto's surface than a candle delivers to the far wall of a cathedral. The sun at Pluto is not a disk, it is a brilliant star. The brightest object in the sky by far, but a star nonetheless. Bright enough to see by, perhaps. Bright enough to cast faint shadows. Not bright enough to warm anything. Not bright enough to power anything. The distance is so vast that comparison almost fails to capture it. Mars, the world that dominates human spaceflight ambition right now, orbits at an average distance of roughly 140 million miles from Earth. Depending on orbital alignment, it can be reached by spacecraft in 6 to 9 months. Pluto, at its average distance, is more than 14 times farther from Earth than Mars is at its farthest. If the trip to Mars is a drive across a large country, the trip to Pluto is a drive across a continent, and then across an ocean, and then across another continent on the other side. The scale is not incrementally larger. It is categorically different. New Horizons, the fastest spacecraft ever launched from Earth, needed 9.5 years and a Jupiter gravity assist, and it was tiny. It was a machine with no crew compartment, no kitchen, no bathroom, no exercise equipment, no medical bay, no radiation vault. It weighed less than many automobiles. It carried enough electrical power to run a handful of household light bulbs. Every gram of its mass had been shaved, scrutinized, and justified. It was an arrow. A message in a bottle fired at maximum speed toward a target that would not wait. A crewed spacecraft is not an arrow. A crewed spacecraft is a building. It carries air, water, food, waste processing systems, power generation and storage, thermal regulation, communication equipment, computing systems, medical supplies, exercise hardware, radiation shielding, structural reinforcement, backup systems for the backup systems, and the most fragile, demanding, and irreplaceable payload in all of engineering: human beings. The mass of a crewed deep space vehicle, even a minimal one, would be measured in hundreds of tons. Accelerating hundreds of tons to the velocities needed to reach Pluto in any reasonable human time frame, and then decelerating those hundreds of tons at the other end, requires a propulsion capability so far beyond anything that currently exists that the gap is not measured in years of development. It is measured in generations of engineering breakthroughs that have not yet occurred, and yet Pluto calls. It calls because it is beautiful. It calls because it was the last planet, the one we fought to visit, the one that rewarded us with a heart-shaped plain and blue skies and mountains of ice as hard as stone. It calls because it sits right at the edge of what we can see, and human beings have never been good at looking at an edge without wanting to cross it. The scientists who studied New Horizons data came away more fascinated, not less. Every answer raised new questions. Is there truly an ocean beneath Sputnik Planitia? What drives the cryovolcanic activity? How old are the youngest surfaces? What is happening to the atmosphere as Pluto moves farther from the Sun on its 248-year orbit? And there are signs that Pluto will not wait for us. Researchers tracking the atmosphere after the flyby have found evidence that it is already changing, already beginning to retreat as Pluto drifts farther from the Sun on its long elliptical path. The world that New Horizons photographed may not look the same by the time anything we send can reach it again. The clock is ticking. And the clock runs on a time scale that makes human planning look absurd. The Persephone mission concept, even if approved and funded tomorrow, would not arrive at Pluto for nearly 3 decades. By then, the atmosphere may have changed dramatically. The surface features New Horizons photographed may have evolved in ways we cannot predict. The urgency is real, but the physics does not care about urgency. The physics only cares about mass, velocity, fuel, and distance. And the distance to Pluto is the kind of distance that turns urgency into something closer to grief. Here is where the story turns. Because everything described so far, the beauty, the complexity, the scientific urgency, the emotional pull, all of that is real. Pluto deserves exploration. It may deserve a permanent human scientific presence someday, in some far future with propulsion technology we cannot yet imagine. But between now and that future stands a wall. Not a wall of politics or funding or willpower, a wall of physics. The distance between Earth and Pluto is so large, the energy required to cross it so extreme, the time involved so punishing, that every system designed to keep a human alive begins to fail long before the destination is reached. The journey to Pluto does not just test a spacecraft, it tests the entire concept of what a human mission can endure. And what the numbers reveal, when you work through them honestly, is something that nobody who has fallen in love with those New Horizons photographs wants to hear. The trip itself is the first thing that will kill you. To understand why the trip to Pluto is not just long, but lethal, you need to understand the difference between distance in space and distance on Earth. On Earth, distance is an inconvenience. A flight from New York to Tokyo is 14 hours. A cargo ship crossing the Pacific takes 2 weeks. These are boring, uncomfortable, occasionally unpleasant stretches of time, but they end. The destination has air. It has food. It has gravity and warmth, and people who will help you when you arrive. Distance in space works differently. In space, distance is not an inconvenience. It is a compounding hazard. Every mile you travel away from Earth adds to the radiation your body absorbs. Every month in transit adds to the bone density you lose. Every year that passes adds to the psychological burden of isolation and the mechanical fatigue on every seal, every pump, every valve, every circuit board keeping you alive. Distance on Earth separates you from your destination. Distance in space attacks you while you cross it. The most energy-efficient way to travel between 2 orbits in the solar system is called a Hohmann transfer orbit. It was described in 1925 by German engineer Walter Hohmann, and it remains the foundational concept in mission planning a century later. A Hohmann transfer uses 2 engine burns. The first accelerates the spacecraft out of its starting orbit and onto an elliptical path that will intersect the destination orbit. The second, at the far end, adjusts the spacecraft's velocity to match the destination. Between the 2 burns, the spacecraft coasts, unpowered, carried only by its own momentum and the sun's gravity. A Hohmann transfer from Earth to Pluto would take approximately 45 to 46 years. The spacecraft would depart Earth, climb outward through the solar system on a long, slow ellipse, and arrive at Pluto's orbital distance nearly half a century later. For a robotic probe, this is merely impractical. For a crewed mission, it is a death sentence delivered in slow motion. No human being has ever survived 45 years in space. No habitat has ever operated for 45 years without resupply. No life support system, no power source, no structural material has ever been tested under continuous space conditions for anything close to that duration. The Hohmann transfer to Pluto is not a mission plan. It is a theoretical calculation that proves the minimum energy path is not an option for human beings. So you go faster. You burn more fuel at departure, trading propellant mass for reduced travel time. This is where every space mission designer confronts the exponential cruelty of the rocket equation. To cut the travel time in half, you do not simply double the fuel. You multiply it by a factor that depends on the exhaust velocity of your engine, and for chemical rockets, that factor grows ferociously. A spacecraft using conventional chemical propulsion, the kind of engines that have powered every crewed mission in history, cannot carry enough fuel to reach Pluto in any reasonable human time frame, while also carrying enough fuel to slow down at the other end. The mass ratios become absurd. You would need a spacecraft that is almost entirely fuel, with a tiny capsule perched on top of a tower of propellant tanks that stretches beyond any engineering reality. Nuclear thermal propulsion offers a partial improvement. Instead of burning chemical fuel, a nuclear thermal rocket heats a propellant, usually hydrogen, by passing it through a nuclear reactor core. The exhaust velocity is roughly twice that of the best chemical engines. This means better fuel efficiency, which translates to either more velocity for the same fuel mass or the same velocity with less fuel. Nuclear thermal rockets were tested on the ground during the 1960s under a program called NERVA. They worked. The technology is real. But even with nuclear thermal propulsion, a crewed mission to Pluto would still require transit times measured in decades unless the spacecraft is accelerating continuously for a significant portion of the trip. Nuclear electric propulsion pushes the efficiency further. Instead of heating propellant directly, a nuclear reactor generates electricity which powers an ion drive or a similar electric thruster. These engines produce very low thrust, but extremely high exhaust velocities, meaning they use propellant with extraordinary efficiency. The Dawn spacecraft, which visited the asteroid Vesta and the dwarf planet Ceres, used an ion drive with an exhaust velocity of roughly 30 kilometers per second, more than 10 times that of a chemical rocket. A nuclear electric system scaled up for a Pluto mission could theoretically reduce transit time to somewhere in the range of 10 to 15 years, depending on the power output of the reactor and the mass of the spacecraft. 10 to 15 years. Say it out loud, and it sounds almost manageable. It is not. 10 years is the minimum. It is the optimistic case, the version that assumes a reactor power-to-mass ratio that has never been achieved in practice, a spacecraft mass that has never been built for a crewed vehicle, and a propulsion system that has never been tested at the scale required. The realistic number, accounting for the mass of a habitable crew module, life support systems, supplies, shielding, redundancy, and the fuel needed to decelerate at Pluto, climbs toward 15 to 20 years for the outbound journey alone. Even the most ambitious robotic orbiter concept ever proposed for Pluto would take the better part of 3 decades just to arrive. For a crewed vessel, the number does not shrink. For a building that keeps people alive, the number does not shrink. If anything, it grows because the added mass of everything humans need pushes the propulsion requirements further up the exponential curve. So, the first fact of a crewed Pluto mission is this. The people who leave Earth will spend somewhere between a decade and 2 decades inside a metal container, crossing empty space before they see their destination. That container is their entire world. Everything outside it will kill them instantly. The vacuum of space is not merely an absence of air. It is an environment so hostile that unprotected exposure causes unconsciousness within roughly 15 seconds and death within 1 to 2 minutes. The temperature in shadowed space drops to hundreds of degrees below zero. In direct sunlight near Earth, it climbs to hundreds of degrees above zero. The container must regulate temperature in both extremes simultaneously, because one side faces the sun and the other faces the void. Inside that container, the atmosphere must be maintained at a breathable composition. On the International Space Station, this is accomplished through a combination of electrolysis, which splits water into hydrogen and oxygen, carbon dioxide, scrubbing systems that chemically remove exhaled carbon dioxide from the air, and trace contaminant control systems that filter out volatile organic compounds released by equipment, food, and human bodies. These systems work. They have kept astronauts alive in low Earth orbit for more than 2 decades of continuous habitation. But they require maintenance. They require spare parts. They require consumable chemicals that are periodically resupplied from Earth. The International Space Station receives resupply missions multiple times per year. Cargo spacecraft arrive carrying food, water, replacement parts, scientific equipment, clothing, medical supplies, and the chemical cartridges that keep the air breathable. If a critical system fails on the station, a replacement can be launched from Earth and delivered within days to weeks. The station is roughly 250 miles above the surface. A crew member experiencing a medical emergency can be inside an emergency room on Earth within hours of leaving the station. A spacecraft bound for Pluto has none of this. There is no resupply. There is no emergency return. Once the vehicle leaves Earth's gravitational influence and begins its long coast outward, it is on its own. Every gram of food must be carried from launch or grown aboard. Every liter of water must be recycled with near-perfect efficiency. Every failed component must be repaired with materials already on the ship, or the crew must find a way to function without it. The engineering term for this is a closed-loop life support system, and the uncomfortable truth is that no fully closed-loop system has ever been demonstrated to work reliably for more than approximately 2 years. The most ambitious attempt was Biosphere 2, a sealed ecological facility in Arizona that operated in the early 1990s. It was designed to be a self-sustaining habitat for 8 people, complete with miniature biomes, agricultural plots, and atmospheric recycling systems. It failed. Oxygen levels dropped dangerously. Carbon dioxide fluctuated unpredictably. Crop yields were insufficient. Insect populations collapsed. Social tensions among the crew became severe. The facility required external intervention to remain habitable. Biosphere 2 was on the surface of the Earth, in Arizona, with a hospital 15 minutes away and engineers standing by outside the airlock. A Pluto-bound habitat would have no such safety net. It would be the most isolated human dwelling ever constructed, operating under conditions that would make Biosphere 2 look like a luxury resort. And then there is the question of sheer mass. Not the abstract mass of propellant and structure that dominates rocket equations, but the blunt, physical weight of keeping human bodies fed and hydrated across a journey measured in decades. A single astronaut requires approximately 1.8 kilograms of food per day. That accounts for the caloric intake needed to sustain a moderately active adult, roughly 2,500 calories, in the form of freeze-dried and thermostabilized meals of the kind used aboard the International Space Station. For a crew of 5, that is 9 kilograms per day, 63 kilograms per week, roughly 3.3 metric tons per year. Over a 12-year outbound transit, the food requirement alone amounts to nearly 40 metric tons. That is 40,000 kilograms of sealed, preserved, packaged nutrition that must be launched from Earth, accelerated to interplanetary velocity, maintained at stable temperatures for the entire journey, and stored in a volume large enough to access without disassembling the habitat. 40 metric tons of food takes up space. It takes up a lot of space. The caloric density of spaceflight rations is high compared to grocery store food, but it is not infinite. You are talking about a cargo hold, the size of a large warehouse stacked floor to ceiling, with vacuum-sealed pouches, cans, and containers, all of which must be organized, inventoried, rotated, and inspected for spoilage across years of storage in an environment where temperature fluctuations, radiation exposure, and simple age degrade nutritional content. Studies of long-duration food storage have shown that certain vitamins, particularly vitamin C and B vitamins, break down over time even under ideal conditions. A ration packed on Earth and consumed 12 years later would be calorically adequate but nutritionally compromised. Supplementation would be required. Those supplements add mass. Their shelf life introduces its own constraints. Water is theoretically recyclable. The International Space Station's water recovery system now achieves a reclamation rate of roughly 98%, processing urine, humidity from exhaled breath, and wastewater back into drinkable water. That 2% loss sounds trivial until you extend it across 12 years. Even at 98% efficiency, the cumulative shortfall over a decade of continuous cycling compounds into a deficit measured in hundreds of liters that must be made up from stored reserves. Carry too little reserve water and you face rationing. Rationing leads to dehydration. Dehydration degrades cognitive function, physical performance, and kidney health. In an environment where every crew member must be operating at or near peak capacity to maintain the spacecraft, even mild chronic dehydration becomes a mission risk. The oxygen budget follows a similar logic. Electrolysis of water produces breathable oxygen, but it requires electricity, which comes from the reactor, which is already burdened with heating, communication, and propulsion demands. Carbon dioxide scrubbing consumes chemical cartridges that have a finite supply. Every breath the crew takes draws down a reservoir that was loaded at departure and cannot be refilled. The mathematics of consumption is simple. 5 people breathing, eating, drinking, and excreting for 12 years produce a logistical footprint that is staggering in its weight, its volume, and its vulnerability to any disruption in the chain of systems that keeps it cycling. But suppose, for the sake of argument, that the engineering problems are solved. Suppose a closed-loop life support system is built that works flawlessly for 20 years. Suppose the food supply is adequate, the water recycling is perfect, the air stays breathable, the structure holds, and every mechanical system performs without catastrophic failure for the full duration of the transit. Even in that best case, the human bodies inside the habitat are still disintegrating. The effects of prolonged spaceflight on the human body are not speculative, they are documented. They have been measured in astronauts returning from missions aboard the International Space Station and, before that, aboard the Russian space station Mir. The data paints a picture that becomes increasingly grim the longer the mission lasts. Bone loss in microgravity occurs at a rate of approximately 1 to 1.5% per month in weight-bearing bones. On Earth, osteoporosis is diagnosed when bone density has declined by roughly 25%. An astronaut in microgravity would cross that threshold in roughly 2 years without countermeasures. The International Space Station uses resistance exercise equipment to slow the rate of loss, and current exercise protocols have reduced it significantly, but they have not eliminated it. Over a 10-year transit, even with daily exercise, cumulative bone loss would reach levels that have never been observed in any astronaut. The long-term consequences of that degree of skeletal degradation are unknown because no human being has ever experienced it. Muscle atrophy follows a similar trajectory. Without gravitational loading, muscles that are responsible for posture and locomotion begin to waste away. The rate of loss can be partially offset by exercise, but exercise in microgravity is not equivalent to exercise on Earth. The body does not bear its own weight. The cardiovascular system, which on Earth must pump blood upward against gravity, loses workload in space. The heart muscle itself begins to change shape, becoming more spherical over time, a phenomenon documented by cardiac imaging studies on space station astronauts. Blood volume decreases. The baroreceptor reflexes that regulate blood pressure when you stand up grow sluggish. Astronauts returning from 6-month missions frequently cannot stand without assistance for hours or days after landing. After years, the deconditioning would be profound. Then there is the problem of the eyes. A condition called spaceflight-associated neuroocular syndrome has been identified in a significant fraction of astronauts who spend extended time in orbit. The syndrome involves swelling of the optic nerve, flattening of the eyeball, and changes in vision that can persist after return to Earth. The cause is believed to be related to the upward shift of bodily fluids in microgravity, which increases pressure inside the skull. Some astronauts have experienced permanent changes in their eyesight. On a mission lasting a decade or more, the cumulative effect on vision is an open question with no reassuring answer. The immune system weakens in space. Studies of astronaut blood samples have shown reactivation of latent viruses, including herpes simplex and varicella zoster, during and after spaceflight. The stress of the environment, combined with altered immune signaling in microgravity, suppresses the body's ability to fight infection. On the International Space Station, this is manageable because missions are relatively short and medical evacuation is possible. On a Pluto transit, a serious infection could become a crew-level emergency with no external medical support available. The nearest hospital would be billions of miles behind them, and the communication delay would mean that even a consultation with a doctor on Earth would involve hours of waiting between each exchange. And then there is radiation. This is the factor that NASA itself has identified as the single greatest obstacle to long-duration deep space missions. It is sometimes called the showstopper, and understanding why requires a brief look at what the space radiation environment actually consists of. In low Earth orbit, astronauts are partially shielded by Earth's magnetosphere, the magnetic bubble generated by the planet's liquid iron core that deflects the majority of charged particles streaming from the Sun and from beyond the solar system. The International Space Station orbits within this protective shell. Even so, astronauts on the station receive radiation doses roughly 100 times higher than the average person on Earth's surface. Beyond the magnetosphere, there is no shield. A spacecraft traveling to Pluto would spend its entire journey exposed to the full deep space radiation environment. That environment has two primary components. The first is solar particle events, bursts of high-energy protons ejected by the Sun during solar flares and coronal mass ejections. These events are sporadic and somewhat predictable. When they occur, they can deliver dangerous doses of radiation in a matter of hours. A crew in deep space during a major solar particle event would need to shelter behind heavy shielding material, typically water or polyethylene blocks, to avoid acute radiation sickness. This is a solvable engineering problem, at least in principle. You build a storm shelter inside the spacecraft and retreat to it when sensors detect an incoming event. The second component is galactic cosmic radiation. This is the one that keeps radiation physicists awake at night. Galactic cosmic rays are high-energy particles, mostly protons and heavier atomic nuclei, that originate outside the solar system. They are produced by supernovae, neutron star collisions, and other cataclysmic events across the galaxy. They arrive from all directions, at all times, with no warning and no periodicity. And they carry enormous energy. A single galactic cosmic ray particle can have the kinetic energy of a baseball thrown at 60 miles per hour, compressed into a single atomic nucleus. When these particles strike shielding material, they do not simply stop. They shatter the atoms in the shielding, producing showers of secondary particles, including neutrons, that can be even more biologically damaging than the original cosmic ray. Adding more shielding material can actually increase the secondary radiation dose rather than decrease it, depending on the material used. This is called the backscatter problem, and it means that simply building thicker walls does not guarantee better protection. There is currently no practical shielding technology that can fully protect a crew from galactic cosmic radiation during a multi-year deep space transit. Active shielding concepts, such as magnetic fields generated around the spacecraft to deflect charged particles, have been proposed but never built or tested at an operational scale. The engineering challenges are immense. The power required to generate a field strong enough to deflect galactic cosmic rays would be enormous, and the superconducting magnets needed would add mass that compounds every other problem in the mission design. The biological effects of chronic galactic cosmic ray exposure are still being studied, but the evidence available is deeply concerning. Animal studies have shown that exposure to high-energy heavy ions, the type of particle found in galactic cosmic rays, causes damage to the central nervous system. Mice exposed to doses simulating deep space conditions showed impaired memory, reduced cognitive flexibility, increased anxiety-like behavior, and measurable loss of synaptic connections in the brain. These effects did not reverse after the exposure ended. They appeared to be permanent. In human terms, this suggests that a crew spending a decade or more in deep space would face not only elevated cancer risk, which is the radiation effect most people think of, but also progressive neurological degradation, memory problems, difficulty concentrating, impaired decision-making. On a mission where every decision could be life or death, and where there is no ground control capable of real-time intervention, cognitive decline is not just a health concern. It is a mission-critical failure mode. NASA currently sets career radiation exposure limits for astronauts based on age and sex, calibrated to keep the estimated excess lifetime cancer risk below a defined threshold. Those limits were designed for missions in low Earth orbit lasting 6 to 12 months. A Pluto transit of 10 to 20 years would blow past those limits within the first few years. There is no administrative workaround for this. You cannot waive the physics of ionizing radiation passing through human tissue. The damage accumulates. The cells either repair themselves or they do not. And over a decade or more of continuous exposure, the cumulative damage would enter territory that has no precedent in human medicine. Now layer the psychological dimension on top of everything else. A crew of perhaps 4 to 6 people, sealed inside a habitat roughly the size of a modest apartment for 10 to 20 years. They cannot go outside, they cannot open a window, they cannot feel wind, rain, or sunlight on their skin. They cannot visit family, they cannot attend a funeral, they cannot hold a newborn child. They can communicate with Earth, but the conversation is not a conversation. It is an exchange of monologues separated by hours of silence. At Pluto's distance, a message takes between 4.5 and 6.5 hours to reach Earth, depending on orbital position. A reply takes the same. A single question and answer exchange takes 9 to 13 hours. This is not communication in any human emotional sense. It is correspondence. It is letter writing at the speed of light across a gap so wide that light itself takes half a working day to cross it. Psychological studies of isolated crews in analog environments, including Antarctic winter overstations, submarine deployments, and simulated Mars missions like the Mars 500 experiment, have documented a consistent pattern of behavioral changes. Social withdrawal, irritability, sleep disruption, motivational decline, interpersonal conflict that escalates in confined spaces with no possibility of escape. The Mars 500 experiment, which locked 6 volunteers inside a simulated spacecraft for 520 days, observed measurable increases in stress hormones, disrupted circadian rhythms, and episodes of social friction that required intervention from the support team. 520 days. That is roughly 1.5 years. A Pluto mission would last 10 to 20 times longer. The psychological pressure would not simply scale linearly. It would compound, the way interest compounds, the way radiation damage compounds, the way every problem on this mission compounds. Because there is no relief valve, there is no port of call between Earth and Pluto, there is no island to stop at, no harbor to pull into, no way to step outside and stretch your legs. The trajectory is a straight line through nothing. The view out the window after the first few months is unchanging. The sun shrinks slowly behind you, dimming from a disk to a bright dot to a point of light that is merely the brightest star in the sky. The stars themselves do not change. There is no scenery. There is no weather. There is nothing to look at except the walls of the habitat and the faces of the same handful of people you have been looking at for years. Human beings are not built for this. We are built for horizons and seasons and novelty, and the social complexity of communities larger than a single household. Strip all of that away for a decade, and you are conducting an experiment in psychological endurance that no ethics board on Earth would approve. And there is one more factor that does not appear in the engineering specifications or the medical studies, but may be the most corrosive of all: the knowledge that you cannot go back. A crew heading to Mars knows, at least in principle, that a return window opens approximately every 26 months. The trip home is 6 to 9 months. Earth is reachable. The return is built into the mission architecture. A crew heading to Pluto knows something different. They know that the journey they are on has consumed a decade of their lives already, and the destination they are approaching does not have the resources to sustain them, does not have the fuel to send them home, and sits so far from Earth that rescue is not a concept that applies. If something goes wrong at year 8 of a 10-year transit, there is no abort. There is no emergency return trajectory that takes less than another decade. The nearest human being who is not inside the habitat with you is billions of miles away and getting farther. This is not the psychology of exploration. This is the psychology of exile, and it begins on the day of departure. The history of human exploration is filled with stories of people who crossed vast distances and endured terrible hardship to reach unknown places. Those stories almost always contain a moment of arrival, a moment when the suffering gives way to discovery, when the horizon opens and the new world appears. What makes Pluto different is that the moment of arrival does not bring relief. It brings a new set of problems that are, in many ways, worse than the transit that preceded them. Because Pluto is not a destination that welcomes you, it is a world that was never meant for human presence. Its surface temperature can freeze nitrogen into a solid. Its atmosphere is a ghost. Its sunlight is a memory. And everything your body and your machines need to survive, warmth, power, oxygen, gravity, is either absent entirely or present in quantities so small they might as well be absent. The journey was supposed to be the hard part. It is only the beginning. Imagine you have survived the journey. Imagine the closed-loop life support held together for 12 years. Imagine the radiation did not destroy your cognitive function. Imagine the bone loss was managed, the muscle atrophy was controlled, and the interpersonal dynamics among the crew did not fracture beyond repair. Imagine every pump, every filter, every seal, every circuit aboard the habitat performed within acceptable parameters for more than a decade of continuous operation in the most unforgiving environment human engineering has ever faced. Imagine all of that went right. You are now approaching Pluto. And the first thing you must do is something that New Horizons, the only spacecraft that has ever visited this world, was never designed to attempt. You must slow down. The deceleration problem at Pluto is not simply a matter of applying brakes. It is a confrontation with orbital mechanics that punishes every kilogram of mass you carry. Your spacecraft has been traveling for years at a velocity measured in tens of thousands of miles per hour relative to Pluto. To enter orbit, you must shed almost all of that velocity. On a mission to Mars, you can use the planet's atmosphere to help. Mars has enough atmospheric density to allow aerobraking, a technique where the spacecraft dips into the upper atmosphere and uses aerodynamic drag to bleed off speed over multiple orbital passes. This saves enormous amounts of fuel. Pluto has no such option. That same vanishingly thin atmosphere, 100,000 times less dense than Earth's, is composed almost entirely of nitrogen with traces of methane and carbon monoxide. That is not thin in the way that Mars's atmosphere is thin. Mars has roughly 1% of Earth's surface pressure, which is enough to deploy parachutes and generate meaningful aerodynamic force. Pluto's atmosphere is roughly 1/500th of even that, which is the same as having no atmosphere at all for the purpose of slowing a spacecraft. There is nothing to push against. Every unit of velocity that needs to be cancelled must be cancelled with onboard propellant, fired from engines that were loaded with fuel on Earth more than a decade ago. The proposed Pluto orbiter concepts address this by using nuclear electric propulsion for the main deceleration, running ion engines for months or years as the spacecraft approaches, gradually shaving velocity in a long, spiraling braking burn. For a robotic probe massing a few thousand kilograms, this is technically demanding but conceptually feasible. For a crewed vessel massing hundreds of tons, the power requirements scale beyond anything that has ever been built for spaceflight. The reactor would need to be enormous by spacecraft standards. The ion engines would need to operate continuously for years during the approach phase without failure. And the propellant, likely xenon gas, would need to have been carried from Earth in quantities that add yet more mass to the total vehicle, which in turn requires more propellant to accelerate from Earth, which requires more propellant to decelerate at Pluto. The rocket equation does not negotiate. It simply multiplies. But suppose the deceleration succeeds. Suppose the spacecraft enters orbit around Pluto after a braking maneuver lasting months. The crew is now circling a world that has been their destination for longer than some of them have been adults. They look down through their instruments at the surface below, and what they see is a landscape that offers them nothing they need to survive and actively opposes almost everything they require to function. But before the crew can confront the surface conditions, they must first reach the surface. And landing on Pluto is a problem that has never been solved, never been tested, and never been attempted by any spacecraft in history. It is an entirely different category of challenge from landing on any world that humans or robots have previously visited, and the reasons go beyond the obvious. On Earth, landing from orbit involves entering the atmosphere at high speed and using aerodynamic drag to decelerate. The atmosphere does most of the work. Parachutes and heat shields handle the transition from orbital velocity to survivable touchdown speed. On Mars, the atmosphere is thin but present. It provides enough resistance to slow a spacecraft from hypersonic speed to roughly supersonic speed, at which point parachutes deploy and retro rockets handle the final descent. It is difficult. Mars landings fail frequently. But the atmosphere provides a meaningful contribution to the deceleration budget, saving fuel and reducing the engineering burden on the propulsion system. On the Moon, there is no atmosphere at all, so landings are entirely propulsive. The lunar module fires its descent engine continuously, managing thrust and attitude to bring the vehicle from orbital velocity to a hovering stop above the surface before settling gently onto the regolith. This works because the Moon's gravity is well characterized, the descent trajectory is short, and the surface is solid rock and compacted dust that can bear the weight of a landing vehicle without ambiguity. Pluto offers neither advantage. Its atmosphere, at roughly 11 microbars of surface pressure, is present in the technical sense but functionally useless for deceleration. It provides no aerodynamic drag that a spacecraft designer could rely on. You cannot deploy a parachute into an atmosphere 100,000 times thinner than Earth's and expect it to contribute anything meaningful. At the same time, the atmosphere is not quite nothing. It contains haze particles. It interacts with the surface through sublimation and condensation cycles. It introduces a layer of uncertainty into the descent environment that would not exist on a truly airless body like the Moon. A lander descending through Pluto's atmosphere would need to account for its presence without being able to use it. It is an atmospheric nuisance rather than an atmospheric resource. This means the entire landing must be propulsive. Every meter per second of descent velocity must be cancelled by firing engines downward. For a crewed lander carrying life support equipment, surface habitat modules, power systems, supplies, and the crew themselves, the fuel requirement for a fully propulsive descent is substantial. And that fuel was carried from Earth through the decade-long transit, through the orbital insertion maneuver, and must now be expended in a single, irreversible event. If the descent engines underperform, if a valve sticks, if a fuel line develops a blockage after 12 years of dormancy, the lander does not have a second chance. There is no abort-to-orbit option that resembles anything in the Apollo playbook. An abort from a Pluto descent returns the crew to Pluto orbit, where they remain in a spacecraft that has just burned a significant fraction of its remaining fuel, orbiting a world they can no longer reach, with no resupply and no clear path forward. Then there is the surface itself. Where do you land? The landing site selection for a crewed mission would depend on data that is, at best, 9 years old, captured during a single high-speed pass that lasted only hours. Surface conditions may have changed in the intervening years. Nitrogen ice migrates seasonally. Frost deposits shift. The atmosphere redistributes surface material over time. A site that appeared smooth and flat in 2015 may not be smooth and flat when a lander arrives decades later. Sputnik Planitia, the vast nitrogen ice plain, might seem like a natural landing site due to its apparent smoothness. But nitrogen ice presents its own hazards. The load-bearing capacity of nitrogen ice at Pluto's temperatures is not well understood. Water ice at those temperatures is as hard as granite and could support a lander without difficulty. Nitrogen ice is a different material with different mechanical properties. It is actively convecting, meaning the surface is not static. The polygonal cells observed by New Horizons indicate that the ice is churning on timescales of hundreds of thousands of years, which is geologically fast. The surface may be fractured at small scales, in ways not visible in flyby photographs. A lander setting down on nitrogen ice could potentially crack through a thin crust into softer material below, or settle unevenly as the ice deforms under concentrated weight. No laboratory on Earth can perfectly replicate the conditions of nitrogen ice under Pluto's gravity and thermal environment to test these scenarios. The crew would be landing on a surface whose structural behavior under the weight of a spacecraft is, in a very real sense, unknown. The terrain outside Sputnik Planitia is rougher. Mountain ranges of water ice, cratered highlands, and regions coated in dark tholin deposits offer poor landing conditions. The low sunlight makes visual navigation during descent extraordinarily difficult. There is no GPS constellation around Pluto. There are no ground-based beacons, no radar reflectors, no surveyed and certified landing zones. The crew would be descending onto an alien surface using onboard sensors, automated hazard avoidance algorithms, and their own judgment, all of which must function correctly the first time, because there is no opportunity to circle around and try again. The surface temperature of Pluto averages approximately -387 degrees Fahrenheit. In scientific terms, this is roughly 40 kelvins on average, fluctuating between approximately 33 and 55 kelvins, depending on location, terrain, and season. To place this in context, the boiling point of nitrogen, the gas that makes up 78% of the air you are breathing right now, is -320 degrees Fahrenheit. On Pluto, nitrogen is not a gas. It is a solid. It forms vast plains of crystalline ice that stretch for hundreds of miles, translucent and pale, frozen so thoroughly that the molecular motion within the crystals has nearly stopped. Sputnik Planitia, the western lobe of Pluto's famous heart-shaped feature, is a basin filled with this nitrogen ice to a depth of several miles. The ice is slowly convecting, warm nitrogen rising from below and cool nitrogen sinking at the margins. But the word warm here means a fraction of a degree above the surrounding material. The entire process occurs at temperatures where most chemical reactions effectively cease. Water on Pluto does not behave like water on Earth. At Pluto's surface temperatures, water ice is a structural material. It does not melt. It does not flow. It does not sublimate in any meaningful quantity. It is as rigid and as hard as bedrock granite. The mountains that New Horizons photographed along the edges of Sputnik Planitia, some towering higher than any peak in the Appalachian Range, are made of water ice that behaves mechanically like stone. You could not chip it with a hammer easily. You could not melt it with any heat source that a crew could practically deploy on the surface. Water ice on Pluto is not a resource waiting to be extracted. It is geology. Methane exists on the surface as frost, coating terrain features in a thin layer that contributes to Pluto's complex coloring. Carbon monoxide ice is present in Sputnik Planitia alongside the nitrogen. None of these materials is useful to a human crew in any direct sense. You cannot breathe nitrogen ice. You cannot drink water ice that is 230 degrees below zero without first expending energy to melt it and then warm it. And the energy required to do this on Pluto is not trivial because the ambient temperature is so far below the melting point that the thermodynamic gap is enormous. Every calorie of heat you add to the environment is a calorie you must generate from a power source you brought with you, because Pluto has no accessible energy of its own. This is the energy problem. And it is perhaps the single most defining constraint of any human presence at Pluto. On Earth, energy is everywhere. Sunlight strikes the surface at roughly 1,000 watts per square meter at the equator. Wind carries kinetic energy. Rivers carry potential energy. Fossil fuels store millions of years of accumulated solar energy in chemical bonds. Geothermal heat leaks from the interior. On Mars, sunlight is weaker but still usable. Solar panels on Mars generate meaningful power. The Martian atmosphere contains carbon dioxide that can be chemically processed into oxygen and methane fuel. There are options. On Pluto, there is one option: nuclear. The Sun, at Pluto's distance, delivers roughly 1 watt per square meter or less. That is approximately 1,000 times weaker than what reaches Earth's surface. To generate the power output of a single modest solar panel on Earth, you would need a solar array on Pluto, covering an area larger than a football field, and it would need to be perfectly oriented toward a sun that appears as little more than a very bright point of light in the sky. This is not merely impractical, It is functionally useless for any purpose beyond the most trivial measurement. Solar power at Pluto does not exist in any engineering sense. Nuclear power is the only option. And the only type of nuclear power source that has ever been deployed on a deep space mission is the radioisotope thermoelectric generator. RTGs work by converting the heat produced by the radioactive decay of plutonium-238 into electricity using thermocouples. They are simple, reliable, and have no moving parts. They have powered every spacecraft that has ventured into the outer solar system, from Pioneer to Voyager to Cassini to New Horizons. They are also astonishingly inefficient and distressingly low in output. New Horizons launched with an RTG that produced roughly 245 watts of electrical power. By the time it reached Pluto 9.5 years later, the output had decayed to roughly 200 watts, a consequence of the steady decline in plutonium-238's thermal output and the degradation of the thermocouples over time, 200 watts. That is less than the power consumed by a typical household television. It is enough to run 7 scientific instruments at low duty cycles. It is not enough to heat a room. It is not enough to run a water recycling system. It is not enough to power the air scrubbers that keep carbon dioxide from accumulating in a sealed habitat. A crude Pluto station would need thousands of times more power than New Horizons carries. A nuclear fission reactor is the only realistic path to generating the kind of power a human outpost would require. NASA and the Department of Energy have been developing a small fission reactor called kilopower, designed to produce 1 to 10 kilowatts of electrical power for surface operations on the Moon or Mars. 10 kilowatts is enough to power a small scientific station in an environment where supplemental solar power is available and where the thermal environment is not 300 degrees below zero. On Pluto, every watt of electrical power that is not used for science or communication must be dedicated to one overriding purpose: keeping the crew from freezing to death. The thermal challenge on Pluto is unlike anything encountered in any other proposed human spaceflight scenario. In low Earth orbit, thermal management is a balance between absorbing heat from the sun on one side and radiating heat into the cold of space on the other. On the Moon, the surface reaches extreme temperatures in both directions, baking in sunlight and freezing in shadow. But the thermal cycling is predictable and manageable with insulation and radiators. On Mars, the average temperature is roughly -80 degrees Fahrenheit, cold, but within the range of engineering experience. Antarctic research stations operate year-round in temperatures that occasionally drop below -100 degrees. On Pluto, that baseline never changes. The cold is not seasonal. It is not cyclical. It is the permanent, unrelenting, default state of the surface. Every surface your habitat touches, every strut that contacts the ground, every cable that runs along the exterior, every sensor that extends outside the hull, is immersed in a thermal environment that will drain heat from any warm object with merciless efficiency. The thermal gradient between a habitable interior at roughly 70 degrees Fahrenheit and the Plutonian surface at -387 degrees represents a difference of more than 450 degrees. Maintaining that gradient requires continuous, aggressive, uninterrupted heating. If the heating system fails for even a matter of hours, the interior temperature will begin to drop. Condensation will form on cold surfaces, water lines will freeze, biological systems will begin to shut down. And unlike a power outage on Earth, where you can put on a coat and wait for the repair crew, there is no external source of warmth anywhere in the world outside your door. The atmosphere that exists on Pluto, thin as it is, adds its own complication. None of those gases are breathable. There is no free oxygen anywhere on Pluto's surface or in its atmosphere. Even if it were somehow thick enough to breathe, the composition would be lethal. There is no free oxygen anywhere on Pluto's surface or in its atmosphere. Oxygen exists only locked in water ice, bound so tightly by the extreme cold that extracting it would require energy-intensive processing, melting the ice, electrolyzing the water, and capturing the oxygen gas while disposing of the hydrogen or storing it for other uses. Every breath a crew member takes on Pluto would come from a supply that was either carried from Earth or manufactured on site using energy from the nuclear reactor, energy that is already in desperate demand for heating, communication, and life support. The atmosphere also behaves in ways that are difficult to predict over time. When New Horizons flew past in 2015, Pluto was still relatively close to the point in its orbit where it receives the most sunlight, having passed perihelion in 1989. Even so, observations from stellar occultations between 2016 and 2019 showed that the atmospheric pressure had already begun to decline. The atmosphere was thinning. Nitrogen gas was condensing back onto the surface as the world cooled on its long outward journey from the Sun. Pluto's orbit around the Sun takes nearly 2.5 Earth centuries to complete, and for much of that orbit, the atmosphere may collapse entirely, freezing out as nitrogen frost and leaving the surface in near-vacuum conditions. A crew stationed on Pluto during an atmospheric collapse would witness the sky itself falling, molecule by molecule, as the thin envelope of gas around them settled onto the frozen ground and disappeared. This atmospheric variability has implications beyond the merely scenic. Surface conditions change as the atmosphere thins or thickens. Frost patterns shift. Ice flows may accelerate or stall. The thermal environment at the surface changes as the atmosphere's insulating effect diminishes. Any long-duration surface operations would need to account for an environment that is not merely hostile, but actively evolving on timescales that overlap with the duration of a crewed mission. Gravity on Pluto presents another category of challenge. The surface gravitational acceleration is roughly 0.62 meters per second squared, which is approximately 6% of Earth's gravity. This is less than the Moon's gravity, which is roughly 16% of Earth's. At 6% gravity, a person weighing 180 pounds on Earth would weigh less than 11 pounds on Pluto. Walking would be possible but bizarre, requiring slow, careful movements to avoid launching yourself into long, arcing trajectories with every step. Running would be essentially impossible in any conventional sense. Working with tools would require adaptation, because every action produces a reaction that is disproportionate to human muscle memory, calibrated for Earth's gravity. More critically, Pluto's gravity is too weak to mitigate the physiological damage caused by the transit. A crew that has already spent a decade or more in microgravity or extremely low gravity would arrive at Pluto and find a gravitational environment so feeble that their bodies would continue to deteriorate. Bones would not remodel, muscles would not reload, cardiovascular deconditioning would persist. The crew would be living in a gravitational environment roughly 1/3 as strong as the Moon's, where Apollo astronauts spent at most 3 days before returning to Earth. A Pluto crew would be there for months or years, having already spent a decade in transit, and the surface gravity would offer their bodies almost nothing in return. Now, consider communication. The communication delay that haunted the transit does not improve at the destination. It remains unchanged because the crew is still the same distance from Earth. But the operational meaning changes. During transit, the delay was isolating. On the surface, it becomes dangerous. Every emergency must be handled autonomously. If a fire breaks out in the habitat, the crew must contain it, diagnose the damage, and treat any injuries before a single word of advice could arrive from mission control. If the reactor malfunctions, The crew must troubleshoot it alone, using only the documentation and spare components they have on hand. If a medical crisis occurs, a traumatic injury, a stroke, a cardiac arrest, the onboard medical officer must act without consultation, because no expertise beyond what exists inside the habitat can reach them before the outcome is already decided. The delay does not just prevent conversation, it eliminates the entire concept of remote support. You speak, you wait half a day, a voice comes back. By the time you hear the reply, you may have eaten 2 meals, slept, and begun a new work shift since you sent your original message. This autonomy extends to every domain of the mission. On the International Space Station, ground controllers monitor every system continuously and can intervene within seconds if something goes wrong. On a Mars mission, the communication delay ranges from roughly 4 to 24 minutes, which is uncomfortable but still allows near real-time troubleshooting for many scenarios. At Pluto, that scaffolding vanishes entirely. The crew is the mission control. The crew is the engineering team. The crew is the hospital. There is no backup. The psychological weight of this isolation compounds everything the crew has already endured. During the transit, at least the crew was moving. There was a destination ahead. There was a sense of progress, however slow. On the surface of Pluto, the motion stops. You are there. And there is nothing around you but frozen nitrogen ice and water ice rigid enough to hold the weight of mountains and a sky so faint that the stars are visible in the daytime. Earth is not a blue dot from Pluto. Earth is invisible to the naked eye. It is too close to the sun to be seen separately, and the sun itself is just a bright star among thousands. Home is not visible from the place you are standing. You cannot point to it. You cannot find it in the sky without instruments. The emotional anchor that every human being who has ever left Earth has relied on. The ability to look up or out the window and see the blue marble, the pale blue dot, the visible reminder that home exists. That anchor is gone. From Pluto, Earth is an abstraction. It is a place you remember. It is not a place you can see. Charon hangs in the sky if you are on the hemisphere that faces it. Pluto and Charon are tidally locked to each other, meaning they keep the same faces pointed at one another as they orbit their common center of gravity. From the Charon-facing hemisphere of Pluto, the moon would dominate the sky, appearing roughly 7 times the angular diameter of Earth's full moon. It would not be comforting. Charon's surface is frigid, cratered, and stained dark at the poles by tholins captured from Pluto's escaping atmosphere. It would hang there, motionless, a monument of ice and stone in a sky full of stars, unchanging from day to day, because the tidal lock means it never moves across the sky, it just sits there. Forever. The Pluto day, the time it takes the world to complete one rotation, is 6.4 Earth days. That means roughly 3 days of daylight, followed by roughly 3 days of darkness, though the terms daylight and darkness carry different meanings here than anywhere in the inner solar system. Daylight on Pluto means the sun is above the horizon. It does not mean warmth. It does not mean brightness in any way that would feel familiar. The illumination at Pluto's surface during full daylight is roughly equivalent to what you experience on Earth in the final moments near sunset, when the light has turned amber and shadows have grown long, but you can still see clearly. That is noon on Pluto. That is the brightest it gets. And when the sun sets, it stays below the horizon for 3 Earth days. The darkness is absolute, broken only by starlight and the faint glow of whatever illumination your habitat provides. There is one element of Pluto's environment that researchers find genuinely intriguing from a scientific standpoint, and that is the possibility of a subsurface ocean. Data from New Horizons, particularly the location and characteristics of Sputnik Planitia, has led some scientists to hypothesize that a layer of liquid water may exist deep beneath Pluto's icy crust. The reasoning involves the way Sputnik Planitia is oriented relative to the Pluto-Charon tidal axis and the apparent density anomaly associated with the basin, which could be explained by a subsurface ocean beneath it. If such an ocean exists, it would be buried under a crust estimated at more than 100 miles thick, kept liquid by residual heat from Pluto's rocky core, perhaps assisted by ammonia acting as an antifreeze in the water. This is scientifically fascinating. It is also completely inaccessible to any crew standing on the surface. 100 miles of solid nitrogen and water ice separate the surface from any hypothetical ocean below. No drilling technology that exists or is plausibly foreseeable could reach it. The ocean, if it is there, is a scientific treasure sealed inside a vault of ice thicker than the distance between the surface of the Earth and the edge of space. Every element of Pluto's environment points in the same direction. The surface is too cold to support any biological or chemical process that a crew depends on. The atmosphere is too thin to breathe, too thin to use for aerobraking, too thin to provide any meaningful protection from micrometeorites or cosmic radiation, and it may not even persist through the duration of a long-term mission. The gravity is too weak to counteract the physical deterioration that the crew has already suffered during transit. The sunlight is too faint to generate power. The raw materials present on the surface, nitrogen ice, water ice, and methane frost, are locked in thermal states that require enormous energy inputs to convert into anything useful. The communication delay with Earth eliminates any possibility of real-time support, mentorship, or emotional connection with the larger human world. And the visual environment, the landscape itself, is a frozen desert lit by the memory of a star that barely qualifies as a light source. Pluto gives you nothing. It does not kill you immediately, the way Venus would, with its 900-degree surface and crushing atmospheric pressure, the way Jupiter would, with its lethal radiation belts, the way the Sun would, with its thermonuclear fury. Pluto is not violent. It is indifferent. It simply does not have anything you need, and it sits in a place so far from anything you could use that the distance itself becomes the deprivation. You carry everything. You generate everything. You maintain everything. And if any single critical system breaks down beyond your ability to repair it, there is no fallback. There is no foraging. There is no adaptation. There is only the slow recognition that the resources you brought with you are the only resources that exist within billions of miles, and when they are gone, so are you. The environment of Pluto does not attack. It withholds. And against withholding on this scale, no amount of human ingenuity changes the underlying equation. Every hour you spend on Pluto draws down supplies that cannot be replenished. Every day that passes is a day closer to the moment when something essential runs out or breaks beyond repair. Every week deepens the exhaustion of systems that have already been running at their limits for more than a decade. And this is where the most devastating realization begins to take shape. Because everything so far, the years of transit, the cruelty of the surface, was supposed to be the hardest part. It is not. What comes after is worse. The real problem is the question that every crew member would carry with them from the moment of departure, the question they would try not to think about during the transit, the question that would become inescapable the moment they entered Pluto orbit and looked down at a world that could not sustain them. How do we get home? The answer to that question is the reason this video exists. And the answer is worse than anything the journey or the surface could inflict. Because the return from Pluto is not a mirror image of the trip out. It is a compounding of every difficulty, every constraint, every margin of survival that was already stretched to breaking on the way there. The return does not solve the problem of Pluto. The return is the problem of Pluto, distilled into its purest and most unforgiving form. And the numbers, when you work through them honestly, do not bend. They do not flex. They do not offer a loophole. They simply close the door. The cruelest feature of a Pluto mission is not what happens when you arrive. It is the arithmetic of leaving. Every mission in the history of human spaceflight has been designed around one foundational assumption. The crew comes home. Apollo was a round trip. The space shuttle was a round trip. Every mission to the International Space Station is a round trip. Even the most ambitious Mars mission architectures, the ones that stretch to 2 or 3 years of total duration, are structured around the principle that the crew departs, arrives, operates, and returns. The return is not optional. It is the load-bearing wall of the entire enterprise. Remove it, and the structure collapses, not physically, but psychologically, ethically, and institutionally. No space agency on Earth has ever launched a crew on a mission that was designed, from the outset, to be one way. And that is exactly what a crewed Pluto mission would be. Not because anyone wants it to be. Not because the planners are reckless or the crew is expendable. Because the physics does not allow anything else. To understand why, you have to follow the fuel. Every kilogram of propellant that a spacecraft carries must be accelerated along with the spacecraft. This is the central lesson of Tsiolkovsky's rocket equation, and it applies at every stage of the mission. When you are planning a one-way trip, you calculate how much fuel you need to reach your destination and decelerate into orbit. When you are planning a round trip, you must also carry the fuel needed to accelerate back out of orbit, cruise home, and decelerate into Earth orbit at the far end. But the return fuel is not free mass. It has to ride along for the entire outbound journey. It has to be accelerated from Earth. It has to be decelerated at Pluto. The same cascading logic now applies in both directions simultaneously. The outbound fuel budget and the return fuel budget do not simply add together. They feed into each other, compounding through the rocket equation until the total mass required for a round trip dwarfs the mass required for a one-way journey by a factor that grows not linearly but exponentially. For a crewed vehicle with the mass of a deep space habitat, the numbers cascade beyond any existing or plausibly near-term engineering capability. A rough estimate of the total delta-V budget for a round trip from Earth orbit to Pluto orbit and back, using chemical propulsion, exceeds 30 kilometers per second. For context, the entire delta-V budget from Earth's surface to low Earth orbit is approximately 9.5 kilometers per second. And achieving that requires discarding 90% or more of the rocket's launch mass as spent fuel and structure. A 30 km per second budget for a vehicle massing hundreds of tons would require a propellant mass so large that the word impractical does not capture it. The word is impossible, not as a failure of imagination, but as a mathematical boundary. Nuclear electric propulsion improves the fuel efficiency dramatically, but it does not erase the problem. It compresses it. A nuclear electric round trip to Pluto might require a delta-V budget of roughly 15 to 20 kilometers per second, depending on trajectory and mission profile. With ion engines operating at the high exhaust velocities that electric propulsion allows, the propellant mass fraction becomes manageable on paper. But the transit time becomes the new enemy. Ion engines produce tiny amounts of thrust. They accelerate slowly. A nuclear electric round trip to Pluto, including time at the destination, would take on the order of 25 to 40 years. The crew that departs Earth in their 30s would return, if everything worked perfectly, in their 60s or 70s. They would have spent the majority of their adult lives inside a spacecraft, and everything would not work perfectly. This is the second layer of the return problem. The spacecraft that brings the crew home is the same spacecraft that brought them to Pluto. It has been operating continuously for a decade or more by the time the return journey begins. Every component aboard has aged. The nuclear reactor has been running for 10 to 15 years. Its fuel has partially depleted. Its output has declined. The thermocouples that convert heat to electricity have degraded. The electrical systems that depend on that power have been subjected to a decade of thermal cycling, vibration, radiation exposure, and cumulative wear. The life support systems that barely held together during the outbound transit must now hold together for another decade or more on the way home. There are no spare parts waiting at Pluto. There is no orbital depot. There is no supply cache pre-positioned by an earlier robotic mission, because no such mission has ever been sent, and even if it had been, the supplies aboard it would have been sitting in the deep space radiation and thermal environment for decades before the crew arrived, degrading in their own way. Whatever the crew has when they leave Pluto orbit is whatever they will have for the entire return journey. If a critical pump fails in year 3 of the return, they must fix it with the tools and materials they have carried since Earth. If a seal degrades and the habitat begins to lose atmosphere, they must patch it with what they have. If a crew member develops a medical condition that exceeds the capability of the on-board medical kit, there is no medevac. There is no hospital ship following at a safe distance. There is only the habitat and whatever is in it. The radiation exposure during the return transit adds to the dose accumulated during the outbound transit and the time spent at Pluto. A crew that has already absorbed a decade or more of galactic cosmic ray exposure would continue to absorb it for another decade on the way home. The cumulative lifetime dose would be unprecedented in the history of human spaceflight. The cancer risk models used by NASA were not designed for exposures of this magnitude or duration. The central nervous system effects, observed in animal studies at deep space equivalent doses, were measured over periods of months, not decades. Nobody knows what 20 to 30 years of continuous galactic cosmic ray exposure does to a human brain, because nobody has ever survived it. The crew returning from Pluto would be the first experimental subjects, and the experiment would be run without a control group, without an ethics review, and without any possibility of early termination. The psychological dimension of the return is different from the psychology of the outbound journey, and in some ways, it is worse. On the way out, there was a destination, there was anticipation. There was the intellectual excitement of approaching an unexplored world. On the way back, there is only endurance. The destination is home, but home is 10 to 15 years away. The crew has already been gone for more than a decade. The people they left behind have continued their lives. Children have grown up. Parents have aged or died. Careers have ended. Governments have changed. Technology has advanced. Culture has shifted. The Earth they are returning to is not the Earth they left. It is a world that has moved on without them. Some of the people they were closest to may no longer be alive. The relationships that defined their pre-mission lives may have faded to the point of irrelevance. They are returning not to a homecoming but to a reintroduction, and the reintroduction will happen after another decade of isolation, physical deterioration, and psychological strain that no human being has ever experienced. There is a concept in long-duration spaceflight psychology called Earth out of view. It describes the emotional shift that occurs when astronauts can no longer see Earth from their spacecraft. Studies of Antarctic expeditioners and submarine crews in extended isolation have identified analogous phenomena. Points in the mission where the psychological connection to the outside world weakens, and the isolated environment becomes the crew's primary reality. On a Pluto return transit, Earth out of view would not be a temporary phase. It would be the permanent condition. Earth would be invisible for years. The crew's entire social universe would be the handful of people inside the habitat. Their entire physical universe would be the walls of the spacecraft. The return trip would not feel like going home. It would feel like continuing to drift, with the only difference being the direction of the drift. And then there is the question that no mission planner wants to ask out loud. What if the crew arrives back at Earth and cannot land? What if the spacecraft, after 20 to 30 years of continuous operation, has degraded to the point where the systems required for Earth orbital insertion and safe re-entry are no longer functional? What if the heat shield has been compromised by micrometeorite impacts accumulated over 3 decades? What if the propulsion system, pushed far beyond its design lifetime, cannot produce the precise burns needed to match Earth's orbit and initiate a controlled descent? The crew would be home in the sense that they could see the planet out the window. They would not be home in the sense that they could touch ground. The cruelest possible ending to a crewed Pluto mission is not dying at Pluto. It is dying in Earth orbit, close enough to see the oceans and the clouds, unable to cross the final few hundred miles. This scenario is not melodrama. It is a direct consequence of the timescales involved. No spacecraft component has ever been validated for continuous operation over 25 to 40 years in the deep space environment. The Voyager probes have operated for more than 47 years, which is a testament to their engineering, but they are not crewed vehicles. They do not maintain an atmosphere. They do not circulate water. They do not scrub carbon dioxide or regulate temperature or grow food. They are simple machines, by comparison, carrying instruments and communicating with Earth. Their survival is remarkable. It is also not transferable to a system of the complexity required to keep human beings alive. Now, zoom out from the engineering and consider the strategic reality. Every crewed space mission that has ever been approved was justified, at least in part, by the value it returned relative to its cost and risk. Apollo justified its enormous expense with geopolitical prestige, scientific return, and the demonstration of national capability. The Space Shuttle was justified, controversially, by its promise of routine access to orbit. The International Space Station was justified by its role as a laboratory for science and international cooperation in low Earth orbit. Mars missions, when they are eventually approved, will be justified by the scientific potential of studying a planet that may once have harbored life, by the stepping stone logic of extending human presence outward, and by the sheer cultural gravity of sending human beings to another world for the first time. What justifies a crewed Pluto mission? The scientific return would be extraordinary. An orbiting crew with advanced instruments could study Pluto's geology, atmosphere, and potential subsurface ocean in ways that no flyby or even robotic orbiter could match. The data would be invaluable. But the same data could be obtained at vastly lower cost and risk by a robotic mission that does not need to eat, breathe, sleep, or come home. The Persephone concept and the Stern orbiter concept demonstrate that robotic Pluto science is achievable within the bounds of current or near-future technology. The argument for sending humans instead of robots to Pluto collapses under the weight of the risk-to-benefit ratio. The crew would be risking their lives, their health, and their connection to the human world for a scientific return that machines could deliver more safely, more cheaply, and more reliably. And this reveals the deeper truth about Pluto. It is not a destination that resists human exploration because of one specific hazard. Venus resists because of its surface temperature and pressure. Jupiter resists because of its radiation belts and crushing gravity. The Sun resists because it is a thermonuclear furnace. Each of these destinations has a specific, identifiable mechanism of destruction. Pluto does not. Pluto's weapon is not heat, pressure, or radiation. Pluto's weapon is distance. And distance is a different kind of killer because it does not strike. It accumulates. Every day of travel adds to the radiation dose. Every month in microgravity adds to the skeletal and muscular deconditioning. Every year of isolation adds to the psychological burden. Every decade of continuous operation adds to the probability of a critical system failure. Distance does not produce a dramatic moment of crisis. It produces a slow, grinding erosion of every margin that separates survival from death. It takes the thin line between a functioning mission and a catastrophe and stretches it thinner and thinner over time until something, somewhere, inevitably gives way. Not with a bang, with a whisper. A seal that was rated for 10 years fails in year 12. A circuit board that absorbed one too many cosmic ray strikes produces an error that cascades through the power management system. A crew member whose bone density has been declining for 15 years fractures a femur while stepping off a ladder. None of these is dramatic. All of them are fatal when the nearest help is a decade away. This is what it means to say that anyone who goes to Pluto will never come back. It does not mean that Pluto will destroy them on contact. It means that the mission architecture required to reach Pluto, operate there, and return exceeds the demonstrated and foreseeable limits of human survival, spacecraft endurance, and propulsion capability. It means that the return leg of the mission doubles every risk and every cost, while offering no new engineering margin to absorb the additional strain. It means that the crew who arrives at Pluto is already at the ragged edge of what the human body and human engineering can sustain, and the return journey pushes them past that edge into territory where the probability of catastrophic failure approaches certainty over the relevant timescales. Pluto is not a wall. It is a horizon. You can always see it. You can always imagine reaching it. But the closer you get, the more you realize that reaching it is not the problem. The problem is what reaching it costs. And the cost is everything. There is a moment that astronauts describe, known informally as the overview effect, when they look back at Earth from space and feel a profound shift in perspective. The planet looks small, fragile, precious. Every human being who has ever lived, every war, every symphony, every act of love and cruelty, everything happened on that small, bright sphere hanging in the darkness. The overview effect has inspired astronauts to become environmentalists, philosophers, and advocates for peace. It is one of the most powerful psychological experiences that spaceflight produces. From Pluto, there is no overview effect. There is no view at all. Earth is not a pale blue dot from Pluto. It is a point of light lost in the glare of a sun that itself is barely more than a bright star. You cannot see your home. You cannot see your continent, your country, your city, or the park where your children play. You cannot even find the correct point of light without consulting a computer. The emotional tether that connects every astronaut to the human world, the visual confirmation that home exists and is real and is waiting, is severed. From Pluto, Earth is a memory. It is an idea. It is a set of coordinates in a navigation database. It is not a place you can see with your eyes and feel in your chest. And that severance, that invisible cutting of the last psychological cord, is the final component of what makes Pluto a one-way destination. Because even if the engineering were possible, even if the propulsion existed, even if the life support systems could last 40 years, even if the radiation could be shielded, even if every technical problem was solved, the human cost of the mission would remain. You are asking people to leave Earth in their 20s or 30s and return, if they return, in their 60s or 70s. You are asking them to spend the peak decades of their lives inside a metal container, separated from everyone they love by a communication delay that makes real conversation impossible. You are asking them to watch their bodies deteriorate in ways that cannot be fully reversed. You are asking them to accept that the world they return to will be populated by strangers who grew up while they were gone. You are asking them to trade a life for a mission, not the risk of a life, the way a fighter pilot risks a life, or a mountain climber risks a life. The actual life itself, the years, the experiences, the relationships. The ordinary human joys constitute the substance of being alive. No one has ever asked that of an astronaut. The Apollo crews were gone for days. Shuttle crews were gone for weeks. Station crews are gone for months. Mars crews will be gone for 2 to 3 years. A Pluto crew would be gone for a generation. And the difference between years and a generation is not a difference of degree. It is a difference of kind. It is the difference between a mission and a sacrifice, between an assignment and an exile. This is the answer to the question that has been building since the first sentence. Why will anyone who goes to Pluto never come back? Not because Pluto is the most lethal world in the solar system. Venus would kill you faster. Jupiter would kill you more violently. The Sun would kill you more completely. Pluto is not the deadliest destination. It is the most remote. And remoteness, at the scale of the outer solar system, is its own category of lethality. It kills you slowly. It kills you systemically. It kills your body, your equipment, your sanity, and your connection to the species you belong to. It does all of this not through a single dramatic mechanism, but through the quiet, patient, relentless accumulation of time and distance acting on every fragile system that separates a living human being from the vacuum of space. Pluto sits at the edge of the solar system, the way a light sits at the end of an infinitely long hallway. You can see it. You can walk toward it. You can even reach it if you are willing to walk long enough. But by the time you arrive, you have walked so far from the door behind you that the hallway itself has become the trap. The door is still there. The light above it is still on. But the distance between you and that door is so vast, and you are so tired, and your legs are so weak, and the hallway is so cold, that turning around and walking back is no longer something your body can do. You did not fall into a pit. You did not trigger a trap. You simply walked until walking back became impossible. That is Pluto. The New Horizons spacecraft, still hurtling outward through the Kuiper Belt more than a decade after its flyby, carries a small canister containing some of the ashes of Clyde Tombaugh, the man who discovered the world it was sent to visit. Tombaugh died in 1997, 9 years before the launch. His ashes will travel with the spacecraft forever, outward, past the heliopause and into interstellar space. They will never return to Earth. They will drift in the darkness for millions of years, long after every human civilization has risen and fallen and been forgotten. In a sense, Clyde Tombaugh became the first person to go to Pluto, and he will never come back. That is not a tragedy. Tombaugh was already gone when the spacecraft launched. His ashes ride outward as a tribute, not a sacrifice. But it is a metaphor that contains more truth than the people who arranged it may have intended, because Pluto is, in the end, a place where things go and do not return, comets that wander too far from the sun, spacecraft that travel too fast to stop, signals that arrive too late to matter, and hypothetical crews who would cross so much space and so much time that the concept of return dissolves from a plan into a wish, into a memory, into nothing. The solar system is vast. It contains worlds of astonishing beauty and terrifying hostility. It contains places that will one day welcome human visitors and places that never will. Pluto belongs to the second category. Not because it is forbidden or because it is inherently more deadly than other destinations, but because it is far. Farther than the human body can endure. Farther than machines can reliably operate. Farther than the emotional and psychological architecture of human life can stretch without breaking. Pluto is the place where distance stops being a number and becomes a verdict. 3.7 billion miles from home, 5.5 hours for a reply, 9.5 years from a spacecraft that was never designed to stop, 28 years from a robotic orbiter that has not yet been built, and a lifetime, a full human lifetime, from any crewed mission that could carry people there and bring them back again. Anyone who goes to Pluto will never come back, not because Pluto is cruel, because Pluto is far, and in space, far enough is forever.